You may have heard Kisters and may not. You will learn a little bit about it later on in a second. But I come from the water industry, but even from a totally different angle. I'm since 13 years in the water industry, but not the water industry that you deal with it on a daily basis. I'm coming more from, not at the end point user, at the end point of the chain. I'm coming more from the source. I'm coming from the natural resources. I'm dealing more with the hydrology sector, because water is happening outside, water is collected and is measured outside and is fed in finally into the water supply systems. The industry that I'm representing here in my talk went through a standardization process which lasts about 3-4 years to standardize data and data exchange between different bodies that participate on the data collection cycle. So I would like to give you a quick introduction into the hydrological cycle, but I think I can keep that short, looking to the audience. I will show you a little bit about Kisters, what are we doing, what are our customers, what are their problems, what are their interoperability issues, what initiatives are already existing to create open standards, and how can you benefit from these achievements that has been made in the hard work that we invested. So, hydrological cycle looks like this. If you go through the forest, you will see one or other element, but you know we have the rivers, we have groundwater charges, we have rainfall, we have evaporation, we have runoffs, and so on. This is how the nature side is looking at. And to measure and to understand this water cycle, we have our monitoring networks in place here. So we have rivers, we have dams, we have weirs, we have aquifers transporting groundwaters, but also we have impacts issues that touches all of us, like floods, like droughts, and so on. And that becomes also a part of influencing the water supply industry in different perspectives. The different series, I think we have long-term observations, so we have long-term data series, time series, let's say 40 years of 15-minute equidistant data on a quite less dense monitoring network. So for instance, we do the Environment Agency of England and UK on a national level. We have 80,000 monitoring points that we have here for groundwater, surface water, information, where if you look at the water supply sector, you have millions of data consumption points, but very short time series only. From the data organization, it's an orthogonal approach here, but with this approach, there is another argument to add on top is that even we are here in the hydrology, the water supply is also within the same industry looking at the hydraulic transportation of data. When we talk about leakages and networks and so on, we have different problems. So that means water, I'm presenting water, you presenting water, water has different perspectives, and I would like to outline some of these and show how we can manage the border from, let's say, from hydrology to hydraulics. How can we feed back data? Because it's called data reuse. It should be a cycle. So Kisters and their customers. Kisters is active in water management since 25 years already, providing solutions for the water management industry. Their key flagship is a water information system, Kisters, a time series management component, and so on. You see this here in the top bar. But we are also active in the energy markets, which do follow much more your patterns of the water supply industry. Here we have anthropogene influence data, we have consumption, we have demands that we have to react on, we have capacities that we need to optimize, we have to measure, and so on. And we are close to the households here. So Kisters is playing, or has several legs into the industries here. Especially the water industry is a global market that we cover from the United States over Canada through Iceland down to Australia, for instance. And our customers are water authorities, flood forecast agencies, hydropower operators, dam operators, so from different perspectives, from legislation level up to down to operational level. The Kisters solution provides products such as gaugings, rating curves, long time series, statistical independent flood peaks and their precise timestamp, for instance, regulation thresholds, direct alerts, flood duration curves, models data, ensemble data, flood intensity, frequency, duration curves, for instance, and long-term values to describe the water regime as a point in time. So these are just examples of the complexity about the data that is collected in hydrology, just to give you a few examples of that. And the purpose is to build a home for this, and Kisters software here, talking architecture-wise, is a 3-tier architecture. We have our own data model, that's fine, that belongs to us. We have a time series server component which is open, which has an open API, proprietary API that can be used by everybody. But especially on the server side here, we have placed the open standards. And I would like to talk about the open standards that we positioned here on our Kisters time series server to serve or to resolve the interoperability issues that are happening within this domain. I would like to make use of reuse a slide from Rob Vertesi from the Bureau of Meteorology in Australia. He has done this in 2007 after the act of strengthen the Bureau of Meteorology as a central data collection point for all monitoring data. That includes irrigation data, water use data, amount of rainfall, the river flows, the dam, reservoir fillings, and so on. And he did an assessment that everybody on water monitoring side, collation and quality assurance side, is very well organized within the organization. There are no issues. So in general, this is done well. But if you look at the information that is created from that data, you see that you can get more out of it finally. So the data aggregation, how is the data aggregated to spatial information? How is it distributed to how can they reuse the information, and when can they reuse it in a repeatable process so that they can understand the data provided. This is done poorly to well, so we see already some decrease in quality here. And finally, the insight, the God status, the forecast, the reporting, the analysis and integration does almost not happening at all in Australia. And this is just not to be tricky to Australians. This is happening everywhere. This is repeatable. You can repeat this, I'm sure, also into the water supply area. Here, this information ladder. You can move it from continent to another position. You have always the same issues, which are called the interoperability issues. And increasing value, of course. So interoperability these days, especially in terms of issues, is actually the separation of data in the hydrology perspective, specifically that you create borders. The borders can be from the organizational perspective or by domain. And especially if you say, okay, I have a groundwater database, I have a surface water database, I have a water quality database. They need to exchange data in between. This is not necessary actually to put actually an actual data domain into organizational borders. So the idea is to open up these borders and minimize the separation of data and ease the exchange processes in between the different products that are used, data management products that are used, also at different monitoring points. There are also issues about legal issues distributing data, especially from, let's say, the environmental perspective. Can I issue raw data which is not validated? Can I issue the last 24 hours rainfall, even if I didn't validated this, it did not go through my quality assurance procedures? Can I issue or disseminate a river stage that contains a peak, which is not a flood peak? Can I make this open for the public to use? And what are the impacts? So there are some legal issues around there, even if, let's say, the technical aspect has been resolved already and data can be exchanged between two bodies. There is still the issue whether they do that because of they haven't processed the data entirely through their partially manual data correction procedures. And of course the description we heard about in the speech before, we must talk the same language. I would say we must talk a similar language, we must use similar terms, we must have lookup tables in place to understand each other, to get the information out of the data that is transported. So the description of objects can differ, that should not be a problem, but they should be aligned to a common conceptual information model, and I think this is pretty much the task in here. So there are standardization initiatives, and we saw already the logo from the QUASI initiative, the Consortium of Universities for Advancement of Hydrological Science, the Open Geospatial Consortium, short terms OGC, especially the Hydro Domain Working Group, OpenMI Association, and we heard about INSPIRE before as well. I would like to quickly run through the activities of this organization. So when we look at the bottom-up approach, let's say from the university, from the academic level, the QUASI found out that all of the thesis, about 40% of the time was necessary to get the data together, to run the actual study. So they wanted to ease that process, and they built up a triangle here, which is headed up by his central system up here that you see at the top. This is a huge catalog that you can query and query for spatial information and say what kind of data do you have in this bounding box. And the quasi central database comes back, I have temperatures here, I have flows here, I have river levels here, and so on. You fill your basket at the end and talk at the end to the hydro server, which is actually serving the physical data. So they built up this triangle, which all of us know. If you open up the browser, you connect to Google. Google is the same as his central here. The actual web page is the Hydro server, and the Hydro desktop here is your browser. So this is the idea there. So what they have done is, next to this triangle, is they defined a service with 3 commands you can get data. Not more, simply easy, handshake process at the beginning. They say, give me station, give me parameter, give me time series data from here to there, and the data is transported in a format that can be easily decoded, and this format was called Water ML10. The OGC, the Open Standard, the Open Geospatial Consortium, has an infrastructure in place to make ISO standards. That's very important, and they did this in the past with GIS data, so they looked at all the interoperability issues between different vendors describing maps, and they came up with web mapping service, web feature service, and so on. Some of you might have heard of this. And now they're looking also at the point, at the measuring point. This could be your flow meter, this could be a data logger that monitors water levels, for instance. Yeah? So they're looking at the point over time. So they had an interest in there, and they looked at different formats that has been created before, and they looked also at Kisters formats like the Environment Agency XML that we've developed, Hydro water data transfer format in Australia, for instance, but also at the Water ML10 created by the QUASI initiative, and they made a new standard out of it, which just became, which is now up for public comments, which is called Water ML20. And Water ML20, you see an example there on the right-hand side, is almost human readable, I would say. It took a while for me to understand what's transported in there, but it's a matter of describing in situ measurements according to the ISO standard of observation and measurements here. So it has elements in there to describe timestamp value, units, and so on, parts of the time series. The data itself is finally transported over a web service called Sensor Observation Service. This Sensor Observation Service is a web service that can live either on the flow meter, it can be a household, it can be an entire database. But if I communicate with such a data node, I simply ask the first question, get capabilities, show me what you have, and it gives me back a catalog. And I can then talk as navigation systems talk that we all use, for instance, Get feature of interest. This is my monitoring point, identified by a number or by a string or by a bounding box or by a name, that depends. And with 2 more commands I can access data already, live, over web services. So this is a sensor observation service. It's a very generic service that is also used to talk to satellites, by the way, that we applied in the Hydro Domain Working Group to get access to databases, to flow monitoring points, to river monitoring points, to get data from A to B in a definable format. And the format is called WaterML 2.0. Coming back from these bottom-up approaches, which are open, everybody can participate there, to the legal perspective. And we heard before about the INSPIRE framework. INSPIRE is the European answer of GEOS, and I do not go into that detail, but the idea here is to have a global Earth observation system of systems, to have the possibilities to get all the global data together in a common software architecture and make the social benefits area, and we are representing at least the water here in that room, or maybe also disasters, yeah, depending on how you look at the waters. For instance, but climate, we are interested in energy and so on. We are representing part of this social or societal benefit area here. And INSPIRE is the answer here as a legislation standards from the European Union. It also looks down spatially, driven by the GIS, to all elements that we have in our water domain. Some of them are shown here on the slides. So we have dams, weirs, we have pipes, we have crossings, we have pumping stations, and so on. They all are standardized, on its way to standardized by spatial data, by the Spatial Data Infrastructure SDI for Europe. And the idea is really to make this data exchange processes repeatable. So that means you must have developed a common language and have a service in place, and at the end a matter of how to transport data. Data is one aspect. The other aspect is really the integration of different optimization tasks or forecast scenarios. This could be modeling, for instance. So OpenMI is also a very mature standard that is used to couple different model technologies together. So it's a standard on exchanging data or result from one model to another. This could be time information, this could be spatial information that can differ. The standard has places for this, so we could plug, let's say, a time series database serving rainfall data to a rainfall runoff model to a river model together from independent vendors written by different people. As long as they are OpenMI compliant, they can react in a chain, and you execute the chain, and the interim results are passed forwards and backwards from one model to the others. Integrated modeling, the examples I gave are within the water domain, but become very more important if you look at the ecological perspective as well, and have integrated modelings there across the domains. Our solutions here that we build as part of our work with the OGC, for example, are our WEBS interoperability solution. So this is an API framework that sits on most of our customers, where you can access with three clicks time series data, such as from the Environment Agency or from the USGS in America, for instance, to exchange data. And also to consume data straight into your application. So you have, on the one hand, you can publish data in a various format, and you can consume data. Then we did some experiments where we won the OpenMI award for this. We sent through the internet, through the OpenMI interface, data to Denmark here to serve a model that sits there. So the technology is not a problem. So OpenMI is applicable, and I have, I think, 2 times already saw the 2 minutes sign here, so I have to rush a bit through the slides. But I think the standardization process is very important. It's really crucial to exchange data and information and to optimize our resource water, and the water industry, at least these are the lessons I learned today, have so many different perspectives that there should not be, within that domain should not be an interoperability issue exchanging data at all, but there are, and I think it is important to get these interoperability issues resolved in a common information model and an open standard that can be applied from all of your vendors, not only from a single vendor, to exchange data between the various components that are capable in the data in the water consumption area. So Kisters at least is a strong partner in that industry. We went through the standardization process and we are happy to participate on applying that standards in different use cases. So thank you very much.